Now we're going to look at the other way that you can multiply two vectors. And this works for both the plane and space. This is a product that results in a vector. So you'll sometimes see this called a vector product, whereas the dot product is called the scalar product because it results in a scalar. But basically, if you have two vectors in terms of ij and k, u cross v is defined as the vector u2 times v3 minus u3 times v2i minus u1 v3 minus u3 v1j plus u1 v2 minus u2 v1k. Now, most people never, ever remember doing it this way. This is a formula that you should not expect to memorize. The most common way that we do this is what's called determinant form. And this is what it looks like. This is called cofactor expansion. U cross v is ijk. You put the vector u here, the vector v here. And basically what you do is you circle the top row, the first column I, cross out everything in its row and column, and then find these smaller determinants here. And then you change the sign to a minus and do the same thing with j and find the determinant of the smaller matrix here. Change signs back to positive and do the same thing with k and take the determinant of the smaller matrix here. And this is what's called cofactor expansion. Now, if you have to do the individual 2 by 2 determinants, this would be AD minus BC. It's the forward diagonal minus the backwards diagonal. Now, you're welcome to work these using cofactor expansion if you've learned that method and you're comfortable with it. Most students for a 3 by 3 matrix prefer the diagonal method for finding these things, for finding the determinant. The diagonal method works with 2 by 2s here, and it works with 3 by 3 matrices. If you're ever trying to find a cross product of something in 4 space, just keep in mind that the diagonal method does not work. You would have to use cofactor expansion. But for our purposes here, we can use this method. So u cross v, and we're going to use the same notation for u and v as we did there. You'll have I, j, and k. We'll write out u1, u2, u3, v1, v2, v3. And this is going to seem a little strange at first, out to the side, I'm going to copy the first two columns, I, u1, v1, and j, u2, v2. And we only need the first two columns here. Okay, so now what I'm going to do is I'm going to draw a forward line across the diagonals, very similar to what you did here. My first one is going to be, and I'm going to put these out of order, u2, v3, I. Then I'm going to add u3, v1, j. And then finally, I'm going to add u1, v2, k. This is why we need those two columns copied. Now, I'm going to go in the backwards direction. And anything I do in the backwards direction, I'm going to subtract. So I'll subtract u1, v3, j. I'll subtract u3, v2, I. And I'll subtract u2, v1, k. And if you distribute all of this out here, you'll see that these two are exactly the same. So let's evaluate the following cross products using this method. So u cross v, we're going to copy down I, j, k. u1 is 1, 2, negative 3. v is 2, negative 2, 1. And then I'm going to copy the first two columns. Okay, so now we do our forward diagonals, and we get 2i plus negative 6j plus negative 2k minus j minus 6i, those two are positive, but remember we're subtracting it, minus 4k. Now I collect my like terms, so I've got 2i and negative 6i, which is negative 4i. Negative 6j and negative j is negative 7j. And then negative 2k and negative 4k is negative 6k. And that will be my answer. For this one, we're going to do the same thing, u cross v. So I'll write I, j, and k. We'll do 2, 1, and 5. And then we'll have 0, negative 4, and 2. I put the 0 there because I is missing. We'll copy down the first column and the second column. And we'll take our diagonals. So this gives me 2i plus 0j plus negative 8k. Going backwards, we'll have minus 4j minus negative 20i minus 0k. So I have 2 minus a negative 20, which is 22i, a 0 minus 4j, negative 8k minus 0k. So that is my answer. Some algebraic properties of the cross product. If we let u, v, and w be vectors in space and we let c be a scalar, u cross v is equal to negative v cross u. That's a very important distinction. Remember, the dot product was commutative, but the cross product is not commutative. U cross v and v cross u are going to have equal magnitudes, but they're going to have opposite directions. U cross v plus w is equal to u cross v plus u cross w, so you can distribute a cross product over a sum. You can move the c between the different vectors. U cross 0 will be the 0 vector. U cross u is going to be 0, the 0 vector. So any vector cross itself is going to give you the 0 vector. U dot v cross w is equal to u cross v dot w. So notice that the grouping here can change and the dot product and the cross product can switch places. Both u cross v and v cross u are orthogonal to the plane determined by u and v. Okay, so this example says find a unit vector that is orthogonal to both u equals 4, negative 3, 1 and v equals 2, 5, 3. So what we want is a vector that is orthogonal to both of these vectors, i.e. the plane determined by u and v. So we want the unit vector in the direction of u cross v. So we're going to first find u cross v, and then we're going to find the unit vector in that direction by dividing by its magnitude. So u cross v, copy down our I, j, and our k. We'll have 4, negative 3, 1, and 2, 5, 3. Copy down the first two columns. So I get negative 9i plus 2j plus 20k minus 12j minus 5i minus negative 6k. And that all adds to give me, let's see, we'll have negative 14i minus 10j plus 26k. The magnitude of u cross v. This is just a vector, so we're finding the magnitude, which will be 14 squared plus negative 10 squared plus 26 squared. So that is the square root of 972, and you can reduce that down to 18 square root of 3. And the unit vector is going to be 1 over the magnitude of u cross v times u cross v. So that'll be 1 over 18 square root of 3 times negative 14i minus 10j plus 26k. And this is going to be negative 14 over 18 square root of 3i minus 10 over 18 square root of 3j plus 26 over 18 square root of 3k. And if you do some simplification and do some rationalizing, you get negative 7 square root of 3 over 27 if I multiply by root 3 over root 3, minus 5 root 3 over 27j plus, oh, this should have been a 13. 13 root 3 over 27k. And that will be your answer. This is the area of a parallelogram with adjacent sides u and v is equal to the magnitude of u cross v. Remember, a parallelogram is one in which you have two sets of opposing parallel sides. So the points going in order here, if you had A, B, C, and D, like so, okay? I'm going to find my vectors and show that we have two pairs of parallel sides. So AB is going to be 1 minus 0, 5 minus 3, 5 minus 2, so 1, 2, 3. BC is going to be 6 minus 1, 9 minus 5, and 5 minus 5. CD is going to be 5 minus 6, 7 minus 9, and 2 minus 5. And then finally DA would be 0 minus 5, 3 minus 2, and 2 minus 2. So since AB is equal to negative 1 times CD, it's a scalar multiple, and BC is equal to negative 1 times DA, we can say that we have parallel sides AB and CD, and you can look at them and tell that their magnitudes are equal, which they would have to be. So AB is parallel to CD and they have the same sides. They're only one difference from each other, so you know they'd have to be equal magnitudes. And we have parallel sides BC and DA, which are also of equal magnitude. So this is a parallelogram. So it says that the area of a parallelogram with adjacent sides u and v is equal to the magnitude of u cross v. So if these two are opposite sides and these two are opposite sides, then you can pick a pair of those adjacent sides, meaning the ones that meet at a corner, and find their area. So I'm going to use, I don't know, let's use DA and CD. Why not? And actually I'm going to swap those two because that's the order that we ended up going in. So AB and CD were parallel, and then DA and BC were parallel. So I'm just going to pick two of them. I'm going to pick, let's see, we'll pick DA, which is this one, to be our U, and we'll pick CD to be our V in this case. So the area will be DA cross CD, and we'll take its magnitude. Okay, so that's going to be the magnitude of this particular vector or cross product. So the cross product here will have I, J, and K. We'll have negative 5, 4, negative 4, and 0, and we'll have negative 1, negative 2, and negative 3. Might would have been easier if I had chosen the positive ones, but it's okay. We'll get through it. So we get 12i plus 0j plus 10k minus 15j minus 0i minus 4k, which is 12i minus 15j plus 6k. And the area is going to be the square root of 12 squared plus negative 15 squared plus 6 squared. And this gives me the square root of 405, or 9 square root of 5 square units. The last concept in this section is the triple scalar product. If we let u be u1i plus u2j plus u3k, and v is the vector with v1, v2, and v3, w has w1, w2, and w3, the triple scalar product u dot v cross w, which we saw referenced earlier, is what happens when you take u, v, and w and find the determinant of that matrix using the diagonal method. Now this is a vector dot a vector here, so this is going to end up being a scalar in the end. And there's three different versions of it due to the nature of the determinant: u cross v dot v, u dot v cross w, v dot w cross u, and w dot u cross v. Now, if you reorganize them in any other way, you may end up with something that has a different sign. It might be the opposite sign, SIGN sign, but the number should be equivalent. And one reason that we're interested in this is there is a geometric property of the triple scalar product. The volume of a parallelepiped with vectors u, v, and w are as adjacent edges is v equals the absolute value of u dot v cross w. So this is a parallelepiped. It's basically a parallelogram that's kind of taken on a prism shape. And you can see you've got the three adjacent vectors here. They're the edges of the corner. So this one says use the triple scalar product to find the volume of the parallelepiped having adjacent edges u equals I plus j, v equals j plus k, and w equals I plus k. Now you may observe that this thing is actually a rectangular prism, but that's okay. That's a special case of a parallelepiped. All right, so the volume we're going to use is u dot v cross w here. And that's just going to be found by a determinant. So we're going to put u first, and I'm just going to make a note outside. This is u, which is 1, 1, 0. V is 0, 1, 1. And w is 1, 0, 1. I'm going to copy the first two columns. Now from here, we just act like any old determinant that we've been finding. The only difference is we're not going to have i's. So forward direction, we'll have 1 times 1 times 1. And we are taking an absolute value of all this in the end, so just kind of keep that in mind. So forward direction, we'll have 1 times 1 times 1 plus 1 times 1 times 1 plus 0. In the backwards direction, we'll have minus 0, minus 0, minus 0. So when you add these together, you have the absolute value of 2, which is 2. So the volume here is 2 cubic units.